Meter diagram. Okay, so welcome everyone for the talk today. It's a pleasure to have Suguman Bansal here. Suguman is a faculty member at Georgia Tech, and her research interests are in the area of formal methods and artificial intelligence. So she has done her PhD and master's from the Rice University and her undergrad from CMI. And Suguman has received several awards like an ADFA Best Paper Award and ECS Rising Star. She was mentioned as the ECS Rising Star. Yeah, over to you, Suguman. So she's going to talk about specification-guided reinforcement learning. Thanks.
Thank you. Thank you, Shivashish, for the introduction and for organizing this on such short notice. This is only my second time at TIFR. The first time I was here, actually my first conference I ever visited was at TIFR. So it feels a little bit like coming full circle. Today I'm going to talk about a recent direction that I've been pursuing, which is along the lines of how does one use formal methods in reinforcement learning. And the idea being, how do we use logical specifications in order to get guarantees or improve the current state of the art in RL? So let's start very, very broadly. As I said, the direction is how do you build trustworthy AI through integration of formal methods and artificial intelligence. And as we know, AI is ubiquitous. As it says, it is shaping our present and future. AI runs smartphones, medical diagnostics, automobiles, transportation, e-commerce, home control systems, social media. It really is no longer the future, it is the present we live in. And AI is so ubiquitous that when I asked ChatGPT to make me a slide for ubiquity of AI, it did a perfectly great job. It's so good that it told me exactly how to build the slide, including giving a very catchy tagline. So AI is indeed ubiquitous, and it is extremely, extremely good today. The only issue is that we cannot trust it. And the failures of the trust of AI, are catastrophic, including legal failures, medical failures, autonomous vehicles. And if you look at all of these are all catchy news headings, but if you really look at what the core is, it is that these algorithms are somewhat opaque. The algorithm just doesn't explain why it made a certain decision. So there is a need to try to build trustworthy AI if we want it to work in safety critical systems. It is okay if ChatGPT tells us how to make a slide, it's not safety critical. But if we want AI to run on automobiles or in medical diagnostics, legal matters, then we want it to be trustworthy. And the direction I take in this is to be able to use formal methods in AI. This audience doesn't need an introduction to formal methods. It has been used for many decades now to build systems that are safe, reliable, trustworthy. The generation one of formal methods was in hardware systems. Today, no hardware is shipped without a proper formal verification pipeline. The same is starting to be true for software systems. Gradually, more and more formal methods is being used before shipping industrial scale software. And the next generation of formal methods research is perhaps how to use formal methods in AI. And with the hope that one could use it for automobiles, for robotics, and other kinds of AI, safety critical AI applications. Now, there are three pillars to formal methods. How do you specify a task specification? How do you ensure a system is correct, verification? And then synthesis, which takes a view that often it is easier to write a specification than it is to design a system from scratch. And if that is the case, can we use formal methods to build a system from a high-level specification of it? And that's the synthesis problem here. And what we are looking at is the synthesis of AI systems. Usually when we talk about synthesis in the context of formal methods, we assume that the environment, the system, the setup in which the system will run in is known, and it is precisely given. We assume that the specification is also given. We know it precisely. And we expect that the system we build rigorously satisfies the specification in the environment it will run. This is usually what we expect of synthesis. when we talk about formal methods. But this is no longer the case for AI systems. In AI systems, oftentimes the environment in which we are working in cannot be specified. For example, if you want to synthesize a robotic system and we want the robotic system to be able to navigate this room, we will not be able to exactly specify all the physical attributes of this room. Right? So environments for AI systems are large, there are uncertainties in it, and there are unknowns. Similarly, specifications are also hard to quantify. How do we express navigation in a room? Right? How do we say that formally in any form of logic? So we're also working with specifications that may be imprecise, maybe non-rigorous, maybe noisy. Sometimes the full specifications are unavailable. How do you synthesize under these specifications? And if the environment and specification are not given rigorously, as we are normally used to, what kinds of guarantees can we get from our systems? Right? Normally, we cannot say that the system will satisfy the specification under all possible cases. What kinds of guarantees can we give if we synthesize AI systems? So this is really what the theme of the work has been. When we're thinking about synthesizing AI systems, what under reasonable assumptions on environments and specifications, what kinds of guarantees can we give? And the specific AI method that I have been looking at is reinforcement learning. Now, you may have heard of reinforcement learning as the third wheel of machine learning. There is supervised learning, there is unsupervised learning, and then there is reinforcement learning. But I like to think of reinforcement learning as a synthesis problem. Because if you think of RL, what it says is that the problem statement is, given a task, can you generate a policy that accomplishes it? Right? And now that's exactly what synthesis is. You've given me a specification, generate a system that satisfies it. RL has found applications in robotics. It's found applications in financial algorithmic trading, software bug finding, and whatnot. So it is a very, very powerful paradigm. But the catch about RL is that, of course, this is not synthesis in the regular sense, so something might be different. The key assumption in RL is that the environment in which the policy will operate in is assumed to be unknown. So we don't know what the environment is. And under these conditions, the way RL tries to learn a policy is by sampling the environment. So it samples the environment returns a feedback, and then based on that feedback, the policy will improve itself. And then this loop will continue until the policy can't be improved any further. So you should think of RL as a policy iteration algorithm that works by sampling and feedback.
But the environment can continue to change over time also. Like
Yes.
you have more and more experience and then
Yeah.
it will change based on whatever past experience.
Yes. So
And so at any point in time, you cannot, maybe we may not be able to say that the policy stops to kind of change any further
Correct.
as well.
Absolutely, right? So this is exactly the assumption that you make, that if you are a robotic system and you start in a corner, perhaps you only know something about the neighborhood of it. As you sample more, you will learn more and more. And the idea being that as you keep sampling more and more, you will learn more about the environment and you'll keep improving the policy. But what is the termination condition? If you sample sufficiently enough that you have learned everything about the environment, then the policy you would have obtained can't be improved any further. So that is the idea behind RL. And we are working in a setting where we assume that the environment doesn't change. It could be that you're exploring more of the environment, but the environment is fixed. So in all of the work that I will talk about, we are assuming the environment is fixed, but it is unknown. Right? So there is uncertainty in the environment. So it could be that if you take an action in a certain state, you could fail. Different outcomes could be possible. It's not that it's a deterministic environment. So there is there is uncertainty and it is unknown, but it is fixed. So we are working in a setting where the environment is fixed. Okay. All right, so this is what reinforcement learning is. It is policy iteration in an unknown environment where you sample the environment to learn the policy. Now, oftentimes, when you talk about RL in the machine learning world, the task is specified in rewards. So suppose you have the task of reaching a certain location, you can set up a reward function for it, which says that if you reach the desired location, you should get a positive reward. Otherwise, you receive a zero reward, right? Or maybe you receive a negative reward if you're heading in the opposite direction. But the issue with rewards is that, well, first of all, they're non-rigorous. Right? The semantics of a reward is not rigorous, unlike what we are used to in logic. So the semantics is non-rigorous, but furthermore, as the task becomes more and more complex, writing a reward function can become cumbersome. For example, it's really easy to specify reach a certain location. But suppose I say now reach P and then reach Q. Now, notice that you can't simply take the reward function of reach P and concatenate it with the reward function of reach Q. Because if you do that, then you will not be able to prevent a behavior that goes from the initial state to Q directly without ever visiting P. Right? Because so now if you think about it a little bit more, then it's actually not very hard to design a function for reach P then reach Q. But you need to start using some global variables, and writing that reward function becomes a little bit more complex. And hopefully this gives you the intuition that as the specification becomes more and more complex, as logical attributes appear in the specification, writing the reward function will become cumbersome. Right? And of course, if the specification is cumbersome and incorrect to begin with, what you will synthesize will obviously not have any kinds of guarantees. So the alternate that people have been looking at in recent times, and this is almost now perhaps a decade long, it's 25, right? So maybe decade or 8 years of this direction of research, where people have been looking at using temporal logics to specify the task as opposed to reward functions. And the benefit, of course, is that they have rigorous semantics and the syntax is close to natural language. So it is preferred over reward functions. For example, if you want to say reach P, then it's eventually P. If you say reach P, then reach Q, then you can say eventually B concatenated with eventually Q. Right? And depending on what exact temporal logic you're using, the syntax will differ, but usually these things are very easy to encode. People have looked at various temporal logics to use, but that's really not the point. The point being that temporal logics have rigorous semantics, easier syntax, and are preferred over reward functions in order to specify tasks. So the question that arises is, what are temporal logics really better than using rewards when you're trying to design reinforcement learning algorithms? If the specification language has changed from rewards to specifications, first of all, we need to design new algorithms for RL. And when we design new algorithms, we want to know what can we say about the theoretical guarantees and how do these algorithms perform. So those are the two things we will talk about today. In terms of task specification, one is rigorous, one is not so much, but how does it fare on the other few parameters? So by the end of the talk, we'll hopefully have filled in this, we would have filled in this slide. And this would be a good point to pause for questions if there are any.
Sorry, I missed this part. Like when
Yes.
you say non-rigorous rewards, what do you mean? Like the user-specified rewards, they may not provide any guarantee.
They may
Like
rewards don't have a rigorous semantics.
Okay.
Right.
In the sense that it's not expressible in the logic that you want to express it in, is that what you mean now?
There's not a rigorous semantic. So in case if you design a reward function for a certain task, you will not really know what reward function, what task you have encoded with your rewards, right? If I give you a logical specification, there's a rigorous semantics, and you can check what are the trajectories that will satisfy that task. With the rewards, doing that is very, very hard, right?
And typically, with respect to these tasks, also there are multiple ways to achieve these tasks, right? And typically, the reward function is trying to somehow find the proxy of saying that this particular trajectory is better than something else. It's just that that is not encodable.
Yes.
Okay.
Yes, exactly. Yeah. All right.
So you can transform the specifications to a reward in some sense, like.
So we will get into that in a bit. And if I don't address the question of can rewards be transformed, can temporal specification be transformed into rewards, please ask me the question again. But we will get into that. And when we talk about theoretical guarantees, we will get into that. Right?
And another question was this. There's a signal temporal logic. How is it different from the standard temporal logic?
So signal temporal logic also has a little bit of a quantitative semantics. And also some of the attributes have, say, within a certain amount of time, continuous time. So we will be talking about discrete time logics here. So we'll talk about discrete time logics. And 0-1 semantics. qualitative. Okay. All right. Cool. So let's start with formally defining what reinforcement learning is. We've built some intuition, but the environment in reinforcement learning is encoded using a Markov decision process, an MDP. An MDP consists of a set of states S and a set of actions A. Note that both S and A could be infinite in number. So we are not limiting ourselves to the case where either of the two is finite. So this allows for continuous domains, which are quite challenging. There is a transition probability, which assigns a probability on how would you transition from one state to another, given an action. And there is an initial state distribution, which simply tells us what are the initial states in the MDP. So, for example, here I have a 9-room environment. Here, the states are given by all of the points in the Cartesian plane. So every point in the Cartesian plane is a state in this 9-room environment. Here, actions are in the form of theta d, where theta is angle, d is a displacement. With very high probability, you transition to the correctly calculated state according to the laws of physics, but with perhaps small probability, you go to a failure state. Maybe the engine fails. We no longer have animation here, but otherwise you would have seen a slight blue dot in one of the corners, and that represents the initial states. It is a continuous state domain, this example. So there are an infinite number of initial states. So there's a distribution on with what distribution saying these are the states from where it is more likely. Now, a policy is simply a map from a trajectory in the environment to a distribution on what actions to take next. So policy is simply informing the learning agent, the RL agent, how to navigate in this room, right? And now, when we are doing reinforcement learning from rewards, in addition to the MDP, you also have a reward function, which assigns a reward on transitions in the MDP. And there's a discount factor, and then you say that the objective of reinforcement learning from rewards is to learn a policy that optimizes the expected discounted sum reward. So we don't need to get into the details of what discounted sum reward is. For the purpose of this talk, it is sufficient to know that because of the discount factor in the reward function, every trajectory has a reward. Intuitively, better trajectory has a higher reward, and worse trajectories have lower rewards. And the objective is to find a policy that optimizes the overall reward. The key thing to note here is that in RL, we assume that the transition probabilities P are unknown. This is the absolute core of RL, right? Because we started by saying in RL, the environment is unknown. And formally, this is what it means, that you don't know what the transition probabilities are. Because if you knew the transition probabilities, then this problem might actually seem very familiar. It's simply the problem of optimization in an MDP. So if you have an MDP, you have a reward function, you have a discount factor, and you know the transition probabilities, and then if the objective is to learn the optimal policy, then there are papers from the 1950s which have solved this problem, and this is a very, very well-studied problem, right? What is also known about this setting is that in this case, the optimal policy will be memoryless and deterministic, meaning you don't need to worry about the history in a policy. It's sufficient to know what the current state is. And you don't need to assign a distribution on actions. You can choose exactly one action. So for this problem, it is known that an optimal policy exists, and it is memoryless and deterministic. And if you know that, then it's very easy to solve these problems. So you set up what are called the Bellman equations, which is really just saying that the reward in the next state is the expected reward from every state. You can do it because it is memorily and deterministic. You can do it in a very Markovian fashion. And once you set up these equations, there are many, many well-known algorithms to solve it. You may have heard of value iteration, policy iteration. All of them are solving exactly this set of equations. But note the key aspect is that in setting up these equations, the probability P, SAT, you need to know the probabilities in order to set up these equations. Right? If you don't know the probabilities, you can't write the Bellman equations. So in the RL problem, we can't use all of this incredible work that has already been done. We need to come up with newer algorithms. So the 10,000 feet view of how RL algorithms work is that, okay, if you don't know what the transition probabilities are, you're given simulated access to the MDP, meaning you can sample the MDP. And what does that mean? It says that if I am the agent learning a policy for me, at every point, I know what my current state in the MDP is, and I have the ability to sample any action from my current state. So when I sample an action from a current state, I can go to a new state and I will be updated that, hey, this is your new current state. And the other thing I can do is that if after sampling, I decide that, oh, maybe I want to go back to the initial state and sample another trajectory, then I can at any time reset to the initial state.
What do you mean sample action? You just choose an action?
Yes, I can just choose any action, right? I can choose any action, and then whatever is the ground truth, according to them, I will go to a new state. I won't know with what probability I transitioned. I will just know what my new state is.
So you know the current state, you choose an action, and
Yes.
you get to know the next state.
Yes, that is it. And I can always choose, I can go back to initial state. So with these two functions, what this allows me to do is that you can sample any trajectory, any number of trajectories of any length. So that is what we mean by you can sample the unknown environment, that you can sample any trajectory of any length.
And
Yes.
Initial state is also a distribution, so at any point you can say, okay, let's go back, choose a state from this
Yes.
distribution.
Yes, yes. So when it's a continuous state environment, then initial state of distribution. If it's finitely many states, you can go back to that one initial state. Yes, yeah.
Like, for example, take the example of a robot trying to traverse this room.
Mm.
Then the state is telling you what the, let's say it's a rover, then the state just encodes what the rover's position is in field.
Yeah, right. So it could say it is these are the X, Y, Z
So if
coordinates.
you're trying to build a system, it is our responsibility to ensure that all possible things, including the rover has flipped or it's in some weird position, we have to ensure that we know all possible states that it can achieve, or is the set of states something that we already know?
So the set of states, you don't need to know them. You will keep exploring them as you go. Right? If you're in a current state, and if I blindly move in a certain direction, I don't need to know. I mean, I'll go there, and according to classical RL, if you hit an obstacle, you'll receive a negative feedback. Right? So that's the feedback you would take, and then you would maybe remember that, oh, if I did that from this state, then I got a negative reward. Right? So you don't need to know the environment. You can explore the environment, but the environment needs to exist.
But if the consequence of like exploring the environment was that the rover got flipped, now
Yeah.
no action is going to lead anywhere.
Yeah. So that's why. So this is a criticism with RL about how does one use it in real world applications. And so really, and you're right? If it's a rover, the chances of a failure in the rover, if the chances are that the rover will, if it's a robotic arm, the arm can break, that's expensive. So in reality, all of this is simulated. So you learn a reasonably good enough policy on a simulation of the environment, and then it's put on the real environment. Right?
So why don't you also have the assumption that suppose you have visited some state? Why don't you have the assumption that you can jump to that state directly? And if you can reset to an initial state, I mean, you could have as well say that, okay, if I have visited some particular place and it's in my memory, and then I can just jump to that state and start exploring from there. I mean, we might not always want to start from the beginning and then.
Yeah. So some algorithms make that assumption that there are certain special, you can't jump to any random state, an arbitrary state. So there may be some special locations that you will want to be able to learn from.
That makes it very strong. Because for any state now you can kind of just repeating that state and
Yeah.
for an action, you figure out the probabilities.
So if you
fairly
visited some of them, then you can say that, well, I might want to.
Yeah.
I visited that. So I have
Yeah.
that.
Yeah.
That's a very strong assumption.
So it's a strong assumption, but you can kind of learn, like if while learning you figure out that some things seem more interesting than others, you can learn an induced distribution, initial state distribution.
Yeah, which might be more efficient or
Yeah.
that way.
Yeah. So if there are portions which seem that also these are interesting, so you can either start with a simulator where you assume you know some more regions, or oftentimes you can algorithmically incorporate that. But this is the basic model, right? Okay. Now, given simulator access to an MDP, the 10,000 feet view of how these algorithms work is that because you can sample as many trajectories of whichever length you wish, very, very intuitively, the 10,000 feet view, this is not how algorithms work, but this is a good intuition to hold, is that what they really try to do is that they try to estimate the transition probabilities. Right? If you sample sufficiently number of times, then you can get a good enough estimate of what the true transition probabilities are. And once you have a good enough estimate, then you can actually set up the Bellman equations. And then you can use your favorite value iteration policy iteration algorithm to obtain the optimal policy. Right? So this is the 10,000 feet view of how our algorithms work. And in terms of guarantees, these algorithms actually do fairly well. If there are finitely number of states, what is known that a basic sampling-based approach can give you what are known as asymptotic guarantees, that if you had the ability to sample an infinite number of times, then you are guaranteed to converge to the optimal policy. And the other kind of guarantee you obtain are what are called as pack guarantees, that there are ways to sample the environment so that you can learn a near optimal policy with high confidence within a finite number of samples. So these are the two kinds of guarantees people care about in the RL. And in terms of what is known in practice, extremely well-established algorithms or extremely competitive algorithms. You can find implementations of extremely competitive algorithms. There are incredible libraries that one can draw from and build upon. So, so reinforcement learning from rewards is actually extremely well-established, both in theory and in practice. Right? So that's exactly where we stand when it comes to learning from rewards. Right? So theoretically, asymptotic and pack guarantees are possible. The question is, what happens if we replace rewards with temporal specifications? Okay. So let's start with the basics. What is reinforcement learning from temporal specifications? As earlier, the environment is given by an MVP, but now the reward is given in the form of a temporal logic, not rewards. And now again, the question is, can you learn a policy that optimizes the probability of satisfying the specification? So we're not trying to optimize a reward now, we're trying to optimize the probability of satisfaction of the specification. For example, in this 9-loop environment, if the specification was eventually reach S1, then any policy that is able to generate these trajectories as shown by the orange dotted line, that would be an optimal policy, right? The key assumption here again is that we assume the transition probabilities are unknown. Right? For those of you familiar with formal methods, if the transition probabilities were known, then this is a well-established problem. This is a problem of probabilistic model checking. Once again, there has been a lot of work in it, and we know how to solve this problem if the transition probabilities were known. And there are well-established algorithms, guarantees exist. You know that you can always find optimal policy, good implementations of all algorithms, all of it is there.
Would it work to replace the reward just by the probability of satisfaction from the state?
Is that not what we're trying to do here? Or is it different? Because the task may not just be a reachability task, it may be something more sophisticated. Okay? The temporal logics let you do that. Okay. It could be a safety objective, it could be a combination. Yeah.
Sorry, just at a high level, how should I think of the temporal specification? What does it mean?
So temporal specifications simply, so for example, you could think of LTL, linear temporal logic. Syntactically, maybe semantically, you can express, you combine predicates with logical constraints. So the temporal predicates would be things like in the next step, I want to see this, or eventually I want to see this, or always I want something to happen. So you can do reachability, you can do safety, it could be a combination of the two, and so on. Right? Okay.
So here, eventually S1 means that you want the take to eventually reach S1?
Yes, you want the policy to be such that trajectories it would produce with high probability will reach S1 eventually. Right? You're not giving a timestamp for when.
Okay.
Okay. So let's try to see what happens in theory. What kinds of guarantees can we get by learning from temporal specifications? And let's go over this with this really simple example. So this is a 3-state MDP. There should have been self loops on the safe and unsafe states, but I was lazy to make them. So the specification here is that it's a 3-state MDP. There's an initial state, there's a safe state, and an unsafe state. The specification is to always avoid the unsafe state, right? And now if the specification is to avoid the unsafe state always, then you can see that there is only one optimal policy in this MDP. And that policy is to take the action A from init, right? Because if you take the action B from init, then there is a small chance that you will transition to the unsafe state and therefore violate the spec. But if you take action A, then with probability 1, you will obviously be safe. So there is only one optimal policy here. And now if the transition properties were known, of course, you could have used one of the many probabilistic model checking algorithms. But suppose we were to try to design a sampling-based algorithm, then here is what we could have done, right? Suppose we knew, if we knew all of the transitions or transition probabilities, we know what the least non-zero transition probability is, right? And suppose that is p-min. Now, suppose I design a sampling scheme that ensures that from every state, I can sample every action about 1 by p-min times, right? Then, with very high probability, if I've sampled every action from every state at least 1 by p-min times, then there's a very, very high chance that I have a very good estimate of what the underlying transition probabilities are, right? And if I have a very good estimate of what the underlying transition probabilities are, then I would have quite easily learned what the optimal policy is. So far, so good?
So you're assuming finitely states and finitely actions.
Yes, for the theoretical guarantee, right? We are starting with the simple case where there are only finite number of states and finite number of actions. Yeah. Now let's see what happens if we did not know the transition properties, right? That is the RL problem. What happens if the transition properties are unknown? All right, so let's do the same exercise. It's the same MDP. There is only one optimal policy. And now we just need to figure out how many times to sample every action from every state, right? Because if we know that, then there is at least one scheme under which we will obviously learn the optimal policy with high confidence. So suppose we say that, all right, I can sample every action from every state k number of times. Then, now suppose let's look at what happens if we sample action B from init. If I sample k number of times, where k is a function of the number of states, the number of actions, it could be a function of anything, but not the transition probabilities, right? So k could be a function of anything, but not the transition probabilities. Now, suppose I sample action B from initial state k number of times. But suppose my MDP is such where the gamma value is much, where 1 by gamma is much, larger than k. So basically k is much, smaller than 1 by gamma. Right? So k is much, smaller than 1 by gamma. What happens if I sample B from init k number of times? It is possible, and with high probability, it is possible that you never see the transition that goes from init to unsafe. Right? If k is smaller than 1 by gamma, that is possible. And if you never even discover that the edge from init to unsafe exists on action B, you might as well learn that taking action B from init is the optimal policy. Right? And that's obviously not the optimal policy. And the issue is that we don't know what the transition probabilities are. So no matter what value of k you give me, I can be an adversary and I can design an MDP. In fact, I will design this MDP. I will just choose my value of gamma to be such that it is such that k is much, smaller than 1 by gamma. So you can actually take this intuition and we can prove that there does not exist an algorithm with pack guarantees when you learn from specifications. If you don't know anything about the underlying MDP.
Seems this problem should occur with rewards as well, right? I mean, you see that. So
That's a very good point, right? Why does this not happen with rewards? And the difference is in the quantitative versus qualitative semantics. When you have rewards in an MDP, what is known is that rewards are robust, which means if you change the rewards slightly, and remember, we were looking at discounted sum rewards. So to answer this question, we'll have to get into discounted sum rewards. So discounted sum rewards is basically over a trajectory, you get the rewards and you will discount them exponentially. So rewards appearing much later have much smaller contribution to the overall reward than immediate rewards. And in that case, if there's a small change in the rewards, then the change to the optimal policy is also slight. Right? However, if you have temporal specifications, temporal specification doesn't really care about the length of the trajectory, right? Eventually, S could be true 1 step away, it could be true 10 steps away, it could be true 10,000 steps away. The probability of satisfying is still the same. No, not the probability of satisfying, the contribution of that execution is similar. So temporal specifications are known to be non-robust. And this is a good example of it because if there's a small change in the probabilities, perhaps that transition would not exist. And if that transition does not exist, then suddenly B becomes an optimal policy. So this is also an example of why temporal specifications are not robust.
I mean, here, sorry, please go.
But for that theorem, are you assuming that we don't know the number of states initially?
You know the number of states,
Oh.
you know the actions, you know the specification, you just don't know the transition properties.
And some like guess and double sort of things cannot be expected.
You can keep guessing, I'll keep making an MDP that.
But the MDP is not like.
The MDP is
transition
fixed.
Probabilities are fixed.
Yes. Yes.
I mean, at some point you have to say, okay, this is not.
Yeah, because listen,
But if I haven't sampled all states, then I won't say that.
But how do you
Yeah.
distinguish between 0 and some small number?
yeah. Right, because the algorithm says within finite number of samples, you need to give an upper bound on the number of samples. Right, and no matter how many, at some point you'll have to say, okay, I can't sample more than this much. Right, and I can choose my MDP to be such where that gamma is small. Right, the issue is exactly that if there's a rare edge, how do you know that rare edge exists? You can reach maybe perhaps a state through some other means, but how do you know of the existence of every rare edge?
I see. I mean, we might have sampled every state, but we might still not have sampled every edge.
You may not have even sampled every state.
You may not have also sampled every state, that's also possible.
But I know the exact number of states before that.
You may
But
maybe
yeah.
the state exists, but you
Yeah.
just don't know if the state is reachable at all.
That's also true, yeah.
For the state is even reachable.
So even if you assume that all states are reachable, you still need to give me an algorithm, right? You will have to determine number of samples beforehand. Right? So that is the key thing, that within a finite number of samples, you can't learn near optimal with high confidence. Right, and this really simple 3-state MDP is enough to prove it.
So when you say probably approximately correct, what is the notion of approximation?
So a policy is a near optimal policy if it's within epsilon, within epsilon distance of the optimal value.
What is that?
So optimal value could be V, and policy is near optimal if its expected probability is greater than V minus epsilon.
Isn't it the case here because except the probability gamma will always be in the same state?
Yeah, but
Yes, sir.
yeah, you don't know what.
It's
Gamma
not
is
the
the
highest one.
You don't know gamma. You can choose epsilon, which is how close you want to be. You can choose your confidence, which is with how much confidence you want to argue, but you don't know gamma.
Yeah, but I know if gamma is large, I will be able to detect it.
Sure, but you
The
don't
only
know.
problem is gamma is small.
It could be, and you have no idea whether gammas are large or small.
That's not what I'm saying.
Okay.
What I'm saying is, suppose if the only problem is with gamma is small, that is the only case when you go to take action V and go to the safe state.
Mhm.
Then I think it's a pretty good policy because with probability 1 minus gamma, it goes to the better state.
But it may not be epsilon optimal according to your definition, right? I mean, when you PAG says that, can you find me an epsilon, given an epsilon delta, Can you find me an epsilon optimal policy with 1 minus delta confidence?
That's my
Right.
confusion. So that's up to a definition of what is epsilon optimal. I can define epsilon optimal to be satisfy the specification with probability something.
With what probability?
1 minus epsilon.
Okay. Then,
So if gamma is smaller than epsilon, I don't care if I take B or A. Because
yes, but your algorithm needs to work on every input, right?
it will work on it.
It will not work on the input where, and whatever epsilon value you give me.
Yeah.
No,
Like
not
gamma-
defined. I mean, the data has to be chosen before
Yes.
the transition probability.
Before knowing what the environment is.
Yeah, I don't see why. So suppose I give you an epsilon.
Yeah.
Okay. I take some 1 over poly epsilon sample. If I find a B, then of course it will work. If I don't find a B, I know that the gamma is smaller than some function of epsilon. So
No, you don't know gamma is smaller than 1 minus epsilon. You only know that with
not
some.
1 minus epsilon, some function of epsilon.
Why is that?
Because if gamma was larger than, let's say, epsilon to the 10, then I would have rejected as 1 over epsilon to the 10 samples.
No, that's also, I mean, that's also a probabilistic statement, right? It's not deterministic.
Yeah, it's probably approximately correct. So you would probably have rejected it in 1 over epsilon samples.
I'm not quite following. So you need to tell the epsilon delta beforehand.
Yeah.
Whatever algorithm you design has to work for every input.
Yeah.
Right? You can't choose your epsilon according to some input parameter that you don't know.
I'm not choosing epsilon.
Yes, but okay, you get some output,
Yeah.
right? And now you're saying that the output is good with respect to some probability that the input had, which you don't know. That's what you're arguing.
Is good.
Right? You're saying that I learned a
Say
policy.
this don't know the instance is fixed, right?
Yeah.
Now for this, epsilon is fixed, delta is fixed, the input is fixed.
Okay.
Now for this instance, you have to be correct with probability 1 minus epsilon,
Okay.
right?
It's here. Look at the chart, right?
No, no, I'm looking for the time.
This word.
Oh, yeah.
Let's do it later. I think it's fine.
Okay.
Yeah, I think this is an input-output problem here, right? We can do this offline. All right. Perhaps we should move. All right, so you can't learn with pack guarantees, but fortunately, there are few assumptions one can make under which you can learn with pack guarantees. And some of the assumptions, so these are a few of the papers that do it. There are a few more talk about it. So some of the assumptions are on the MDP itself. So if you knew, for example, the minimum non-zero probability, or you had a lower bound on the non-zero probabilities, that would be sufficient, right? That's the exercise we did initially. Or if you knew the topology, for instance, right? Topology meaning you know which all transitions are non-zero probability. If you knew the topology, once again, you can prove that you can learn with pack guarantees.
Sorry, what do you if you know the topology?
You know what the non-zero transitions are. You don't know what the values are, but you just know whether it exists or not.
Okay, you know about their existence.
Yes. Yeah. So you know the graph structure, right? You don't know properties. That's also sufficient. Similarly, if you say that, all right, maybe I'm not looking at MDPs which allow arbitrary horizon trajectories. If you limit yourself to MDPs with a fixed horizon, even then you can show that pack is possible.
Sorry, could you repeat the last one?
The assumption is if you fix the horizon of the length of trajectory. So all trajectories have to be of length at most edge. Right? And the edge is predetermined. Right? And the idea there being you don't run into this measure zero problem. So backward induction works. And similarly, if you start making, so there is an argument that you can, making assumptions on the MDP is not right because all of these are very, very strong assumptions from the RL perspective that you know too much about the environment. So what we've been looking at is to say, well, perhaps if you make assumptions on the length of the trajectories that you can sample. Right? So this is no longer an assumption on the MDP, it's an assumption on the length of trajectories that you sample. Under those assumptions, you can also prove pack is possible. Right? And the other question that people look at are what about asymptotic guarantees? Pack is nice, but what about asymptotic guarantees? And there, people have shown that it is actually possible to learn with asymptotic guarantees. And the idea being that if you had the ability to sample indefinitely, then you would have learned the underlying transition probabilities very, very well. Perhaps an interesting thing here is that the current algorithms are actually not very implementable. All of these algorithms depend on some of these pack algorithms under assumption. So something that one should think about is can you design more direct, more simple asymptotic analysis algorithms. And I'll be happy to talk about this offline. So we are pressed on time, but maybe I'll just breeze through what we know about the algorithmic performance. With rewards, what is known is that they are very good at learning tasks with short horizon, but they're quite poor at learning tasks of long horizon. And the real, if you think about how these algorithms are designed, so going back to your question, Subhashish, most of the learning algorithms that learn from temporal specifications actually reduce the specifications into a reward of some kind. And then they use some existing off-the-shelf algorithm that learn from rewards. The issue is that this translation we have proven is not faithful. Not faithful, meaning what is optimal here? Like we can prove that there is no translation from specifications to discounted sum rewards, such that optimal with respect to discounted sum rewards is optimal with respect to temporal motion. So we've been able to prove that such a translation does not exist.
No, so, sorry. I mean, like optimal with respect to the what means optimal with respect to the words which satisfies the specification.
So what the template that algorithms use is that they take an RL from temporal specifications problem and reduce it to a problem of RL with rewards. Now, in this translation, you may modify the environment, you may modify the specification, right? So you can modify whatever is possible. And we've shown that under no modifications, there is no translation that can ensure that this problem, which is optimizing some reward, right? It's finding the optimal policy with respect to a reward, is also optimal with respect to the probability of satisfying the execution. Right? So there is no translation that can do that. But people still do it because they actually end up having fairly good performance in practice. But even there's a question on how well they do. And we have this really nice experiment where we show this is a really simple, it's the same kind of environment we've been looking at. It's a 9 noons environment. If you say the task is to go from S0 to S1 while avoiding the obstacle, S1 or S2, then this graph shows the performance of several state-of-the-art algorithms. X-axis shows the number of samples, Y-axis shows the probability with which the policy learned after X number of samples satisfies the task. And you can see that when the specification is short horizon, visit S1 or S2, it does fairly well. Most of the algorithms learn very, very well, right? So the higher the graph, the closer to the Y-axis, the faster it's able to learn an optimal policy with high probability.
Sorry, I sort of maybe missing this slide. So what you're doing here, so you have those specifications, visit S1 or S2 while avoiding it.
Yes.
And you were saying that you kind of translated this specification, like it's a temporal.
So these are state-of-the-art
which are
algorithms, yes. They do some translation to rewards.
To rewards, and then you were, okay.
Yeah, right? And they do pretty well, most of them. But if you make the specification one bit harder and you say, well, after visiting S1, S2, go to S3, then I have not forgotten to plot here. This is actually what the performance looks like, right? It vanishes. And now one would think, why? And the real reason is that when you try to visit either S1 or S2, it's actually, all of these algorithms end up learning how to visit S2, because between S1 and S2 is easier because it's an obstacle-free path. Right? If you had to visit S1, maybe it can be done, but you need to learn how to navigate around the obstacle. However, when you have the second specification, in order to visit S3, you can only do it via S1. Right? So turns out most of these algorithms completely lack this higher level vision, that maybe some tasks may be harder in the short horizon, but they are better for the long horizons satisfaction of the task. So what we have looked at is we have designed this algorithm that can actually leverage both the high-level specification, which gives you that high-level view, with low-level properties of RL, that it's really good at learning short horizon tasks. And we're able to show that we can design algorithms that can learn very, very sophisticated algorithms. We don't have too much time, so I'm going to breeze through this part. I'll be happy to talk about these separately. So the specification language we're using is called Spectral. It has reachability specifications given by eventually. You can say safety specifications given by always. You can concatenate them and you can use disjunction among them. And without going into details, I'll quickly,
So,
Yeah.
What was the title of the high level specification and low level RL?
yes.
So, what do you mean by low level RL?
Low level RL is off the shelf discounted sum reward RL.
Oh.
So at the high level, we want to use a specification to say, oh, these paths are possible, so perhaps explore them, even if the initial few paths. So the idea is that we'll design a compositional algorithm here, and then you can use the specification to decompose it into accessible small tasks. Each of the tasks is short horizon, so an existing RL algorithm can learn it. Learning from rewards, it can learn it. And then again, you come back to the abstract, you come back to the high level structure to see how you combine these low level tasks in order to satisfy the high level task. So it's a compositional algorithm that uses the specification to decide how to decompose and how to compose, and low level RL to decide how to solve individual subtasks, right? But the argument here is that we can show that for even very, very sophisticated, very, very long horizon tasks, we perform extremely well. So here, this is a 16 rooms environment. It's bigger than the 9 rooms environment. The red blocks are obstacles, and our tool is called DIRL. So it's represented by the dotted blue line. If the specification is box A to B, I'm going to use the shorthand box X to Y to show this, to show the specification of visiting either one of the corners and then visiting Y. Of course, while avoiding obstacles. So if the specification is box A to B, you can see that DIRL does the best, but other algorithms do fairly well. It's still a short horizon specification, relatively. But as you make the specification longer and longer, it could be box A to B, then box B to C. You can see that gradually the performance of other algorithms degrades while DIRL is able to maintain consistent performance across specification complexity. And then what we're also able to show is that it scales pretty well also in the complexity of the environment. So previously was complexity of specification, this is complexity of environment. Again, DIRL is able to fairly well here, while others don't. And another thing that we've been looking at recently is a persistent problem with reinforcement learning is that it's able to learn a policy for the specific task on the specific environment that we're given. Any changes to the environment or this policy or the specification results in absolute failure of adaptability. You can't adapt the same policy. So we've been looking at the question of, can we use specifications in order to learn generalizable policies for reinforcement learning?
And isn't that how it should be? Like, because if you have a specification,
Yeah.
according to the specification, you have a policy.
Yes.
Now the specification changes, the policy should also change.
Yeah, but if my
why should the policy remain the same?
Yeah, correct. But if the specification is from A go to B, and my next specification is from A go to B plus epsilon,
Yes.
you don't want to learn from scratch, right? I mean, if that's how humans were learning, it would be a terrible world, right? At least a very different one. So the idea is that, yes, you're right. Normally when people talk about generalization RL, this is exactly the problem, which is how do you specify what tasks can be possibly extrapolated to, right? You can't have ultimate intelligence. So that's exactly what we say. We say that it is because we're using logical specifications, you can start defining tasks which are similar. So maybe they have similar logical structure, but they differ in the low-level predicates. And those are the kinds of problems we can generalize to. And we have been developing these algorithms where we actually show that we can generalize fairly well. And here is an example I like talking about. Suppose you have a robotic arm, you wanted to displace a tower of blocks from one location to another, and you know how to displace the top 2 blocks, you should be able to displace the remaining tower, right? Because the task is very, very similar, except that maybe the specific location of the initial block and the final block are different. But otherwise, they're very similar tasks. And we've been able to show that by training only on few of the top few blocks, we can extrapolate it to the remaining few. So the blue ones here are what we train on, and the red ones are what we extrapolate to. And this work is appearing at Atwa. So we are very excited about this work. And here we've also been talking about how do you formally quantify generalization? I mean, otherwise one would just talk about how many tasks you can extrapolate to. So we have a notion based on certificates where we try to give a more principled approach to evaluate generalization across tasks. So in terms of algorithmic performance, rewards are great in short horizon, but poor in long horizon. However, temporal specifications are extremely good at long horizon learning. Plus, the fact that we use temporal specifications also facilitates generalization, which is a pertinent problem in RL. Do we have some more time? We don't really have more time, but perhaps I can talk about a few future detections. So the algorithmic template of practical algorithms is still very much, yes, we add a layer of compositional approaches, but at the core, it's still reducing to some problem of learning from rewards. What could be a promising direction of future research is if we can design practical algorithms that directly learn without going through the reward route. If we could do this, we could perhaps design algorithms which are much more scalable in practice and have better guarantees. Another question that is of interest is whether we can verify the policies that are learned. These policies still work in an unknown environment. Currently, algorithms don't have guarantees, but can we design verification techniques in a black box that can give you some kinds of guarantees? And with that, I would like to conclude the talk. Thank you.
Questions? Yes.
Sorry, I think I sort of lost so the case where the specification was digit S1 or S2 by ordering 4, and then we added and digit 3. Why was putting what the specification is, and if the policy just learns to go to S2 and then S3? You are matching the specification, right? What was the
So the way the problem was designed, going from S2 to S3 was not really possible, right? Because to go from S2 to S3 anyway,
law?
such.
Okay.
It's just the way we designed it.
And in the transfer possibility statement that there are no generic ways to transfer performance in RL to performance in specification. That was, should I think of it as there are tasks, like there exist tasks where this is not possible, or for any task I can design a slight perturbation so that this won't work.
So all of this is empirical, right? When it comes to generalization, there is no work that is theoretically backed. All of this is based on empirical performance. And what has been noticed is that RL learns extremely non-generalizable policies, right? So what we've also, I don't have plots here. So actually, okay, this is a good example. So here, the goal, so the source keeps changing, but the target remains same. So you could have a task to go from R0 to the target, R1 to the target, and clearly these are they're close to each other, right?
Sorry, my question was not about the generalization.
Sorry.
The transfer theorem or something. You can't have a generic way to port RL reward
I see.
algorithms to this thing that you can't ever have any guarantee of.
You don't have a translation of RL from temporal specifications to RL from rewards, discounted sum rewards, such that optimal policy with respect to rewards is optimal with respect to specifications.
Does this also say that it's not possible to have some translation which works for most cases or something? Is it how brittle is this impossibility?
So this impossibility already happens for reachability, and reachability is a very simple specification in the hierarchy of temporal specifications.
I see.
I think one can write a similar proof for safety. If you can't do safety reachability, you can't.
So I had a question about generalization. So the thing is, if we assume that the transition probability is very slowly across, then the existing RL policies, are they not robust to this sort of small? Is that what you were trying to? So that's
So we weren't talking about changes, like small changes. Like what you're talking about is what if the transition properties change slightly? Maybe it'll work, maybe it'll not. One really needs to just evaluate these things. And that is partly why generalization is a hard problem, even when you're learning from rewards. What seems like a reasonable adjustment could end up being the policy might have to be quite different, but because rewards are robust, it could be the case that under very, very small changes, the policies might still work out. So the kinds of things we were looking at, we thought these were small changes, which is if you change the initial location slightly, it should work, but it doesn't. So this is the performance of one of the state-of-the-art tools that learns from rewards or specifications on this task that we've trained it for R0 and R1, and we want to see what happens to the remaining. So this is the plot from R0, it's what it learned on, and these are the plots on the remaining. So they're very off from the target. Yeah. So these seem like very small adjustment to the task, but no, these are not adjustments in the transition probabilities. It actually changes the initial state.
Could you repeat what this sorry, like this?
So these are the trajectories of policies. So this is the policy that it trained on, it's for R0. And the train policy went to the target. But then for the remaining policies, we wanted to extrapolate that policy. So we said, is this generalizable? The policy that you've known, will it work if I shift the initial state slightly? And they did not reach the target. Right? So this is a very small change. At the task level, it's a very small, or it really is an epsilon delta difference. And even these overlapped. Right? And this is a Cartesian plane, it's the simplest environment, still doesn't work. So we've been, and this is again performance on another tool. So is that. Right? And when you try to learn generalizably, things can go completely haywire, or they'll just learn well on the training tasks and not extrapolate. So we've been able to show that we can design.
On the top one also, you just change the initial state.
Yes, yes. All of these are plots on some, so ARS, ML, HER, these are all generalizable RLL approaches, which are known in the reward setting, they are known to be generalizable. But the issue is that classic ML does not talk about what they mean by generalization. The definition is very, very vague. It simply says that I will train on a distribution of MDPs, and that's about it. Right? So instead of training on one MDP, you're training on a distribution of MDPs, and we haven't understood why it doesn't work or why it works.
And in one of the slides, you were talking about certificates. So
yeah,
what sort of certificates you were talking about?
So here we're talking about certificates in the sense of so in MDPs, you can certify, when the MDP is known, you can certify tasks using, say, ranking functions if it's a reachability specification, barrier function if it's a safety certificate, if it's a safety task. What we were looking at is, can you define certificates for generalizability? Right, and here the task is similar.
So in an MDP in general, when you say a certificate, it's a policy which you, what is the certificate?
Yes, so for a reachability task,
yes.
The certificate is what is called a ranking function.
Okay.
Right, it simply tells how far you are.
Okay.
Right? Intuitively, one ranking function is the distance, stochastic distance. Like if you're using this policy at some state, are you reducing the distance to the goal with every step? Similarly, for safety, it's a barrier certificate. So if you're close to the unsafe barrier, it will kind of say, oh, you're unsafe. If you're away from it, it will say, yeah, you're all right. But these are all in the non-generalizable setting. So we were looking at, can you define certificates for generalization under our definition of similar tasks. So we have formally defined a notion of tasks that are similar, along which one should be able to generalize. And on those tasks, we have defined what we mean by certificates. Yes.
So you talked about objectives like A and then B.
Mm-hmm.
So how do you translate rewards in practice? Because you need some amount of memory. You need to know that you visited everything. So how do you represent that using this expected discount?
So you can, right? Because the discount sum, that's how you can define your reward. You can say if A has been reached, then assign B. If you reach B, then assign 1.
So
if A has not been
directly
reached,
goes to B, it does not get reward.
yeah, you can design schemes. So the way they do it in practice is that whatever specification is, they'll turn it into some automata form. And then on the automata, they will assign.
Only on the parts which visit A first.
Right. So if you have, say, A visit A and then B, then if you look at its automata, every accepting transition will have that property. Right. So you're only assigning reward to those, everything is getting a 0. So there are ways of translating it automatically.
But that is like having some memory, right? Because
Yes.
automaton itself works as a.
Yeah. So the reward, that's a good point. So the reward is not strictly, so on the slide, I just showed it as reward in one transitions. But we do account for when I said the translation, we do account for, so in the literature, they are called reward machines. Yeah. So the argument is that you can't design a reward machine with finitely many states where this is possible.
Okay. So if there are no more questions, let's thank the speaker.
Thank you. How do we do this? Do we turn it off?
Yeah, you can. Yeah, you can stop it. Yes.